Okay. Good afternoon. My name is, last name is Nandakumar. It's very long, but I go by the nickname Kumar. So feel free to call me Kumar, and if I'm not paying attention, just yell out to get my attention. I would like the class to be fairly interactive, meaning I want to make sure that the pace that I am delivering the material is appropriate. So if there are no questions, if you are very silent, I'm assuming that you're following everything that I'm saying, and then I'll just continue to accelerate. So if you feel that I'm going fast, you need to slow me down and ask questions. It's a very good way of slowing down and making sure that you understand whatever concept that I'm introducing in this course. Okay, so this is about computational technology in chemical engineering. It's a one credit course, so we meet once a week, Tuesdays, 12:30 to 1:30, and every week I will put up an assignment on Moodle. I noticed some of the more enthusiastic ones have already gone into Moodle and checked out the course web page and followed some of the instructions in there. But others, I would recommend very highly that you look at Moodle as the source or distribution of any material in this course. You will find this document called the course outline, and it basically spells out all the rules, assessment procedures, what we will cover, and the office hours and things like that. I will briefly go through some of the important material in this document. Otherwise, I would ask you to go through, download, and read the document by yourself. Now, the prerequisite for this course is Math 1550, so if you don't have it, you need to take appropriate action. I have office hours once a week on Fridays from 1 to 3 or 1 to 4. So my days in the week tend to be pretty occupied on Tuesday, Wednesday, and Thursday. Tuesdays and Thursdays I have classes, and Wednesdays I have meetings with my graduate students, but Mondays and Fridays are pretty much open. I don't have any regularly scheduled activity. So you are always welcome to drop in anytime, even if I have somebody in my office, if you're just willing to wait for some time, I'm willing to attend to you. So I normally operate, I guess, in an interrupt mode. So I have an open door policy. In addition to that, what I'm saying here is the office hours is exclusively for this. So during this time, I won't entertain interruptions from anybody else in the department, but it is exclusively meant for you. Of course, I'm keeping the shop open. Nobody is there. Or one of my graduate students wants to talk to me, of course, I will entertain that. But as soon as the student comes in, I will listen to you. Okay, so there are no, my office is in Chemical Engineering Building, 210. And there is no prescribed textbook in this course, but I would recommend that you look at two sources, acquiring two sources. One is this book, A Practical Introduction to Programming and Problem Solving Using MATLAB. Okay, so it's a very good book and a fairly inexpensive book, about $33 for the e-edition. You can download it from Amazon. There is a Kindle version. And you don't need to have Kindle. There is a Kindle reader for almost any computer that you can think of, tablet or PCs or Mac. So it may be worth investing. But a better investment might be to buy a student edition of MATLAB, which comes with a software itself. Okay, so you could install it on your own computer and work from home. And that is about $80 from Amazon. Amazon normally advertises both a new and a used edition. Don't buy a used edition because when you get the disk, you need to register the disk online with MathWorks, the supplier of the MATLAB. So if you buy a used edition, the license may already be used up. Okay. So you may not be able to use that. So buy a new edition. It is about $80. It's worth investing that. Okay, and other than that, every lecture notes for every class, I will put it ahead of time on Moodle, so you can download it if you want and print it out, and then you can annotate it in the class. My philosophy, I guess, in the class is I want your undivided attention to what I'm saying and engage with me in discussion. Because if you have a reading material, you can always read on your own. Okay, and when I was a student, and I still, many of you probably do that, is try to take notes as much as possible, as fast as you can. That is, take down everything on the board into your paper, because you will not have access to it after that. Okay, that is not true in this course, because I give you the notes beforehand. You can download it, and if you choose to write down a few things, annotate a few things, that's fine. But whatever I annotate, whatever I write on this, I will put also a copy of that PDF file after the lecture onto the Moodle. Okay, so I want to minimize your note-taking and maximize your attention to what I'm saying and engage in discussions with me, ask questions. Okay, particularly if things are not clear, if you're not able to formulate a question, just ask, Kumar, repeat that, I don't understand it, that's fine. Okay, don't think that you are the only one and everybody else understands it. I have the problem as an instructor. If nobody asks any question, I would stop and say, do you understand? Okay, that's the only question that I can ask. Okay, and if there is absolute silence, what is the interpretation? I'm going to interpret as you understand, and then I move on. And so, sometimes I may ask a question that is, leave out something unexplained, and then say, can you guess what that might be? And the first person who gets it and answers, I assume that everybody understands it. Okay. Again, I try to minimize making these errors, but it's in your hands to stop me and ask questions and engage in the discussion. Now, I also have a habit of recording the lectures. Okay, what I mean by that is whatever is happening on the board, whatever I write on this, will be captured along with the audio and the video, and it will also be uploaded into Moodle every lecture. And so that is an MP4 file. You can choose to download it onto your iPad or tablet or your computer and can listen to the lecture. Okay, if there are, when you have 15 minutes, and particularly during lunchtime, you might doze off from time to time. So you want to go back and say, what did you really say? You want to listen to a certain part. That option you have. Okay, and I also have on YouTube a number of other lectures that I've given in the past, courses. One of them would be 2176, which is a follow-up course to this. That's also on YouTube that you may want to listen when it covers certain topics, because I have introductions to MATLAB in that course as well. Now, the assessment is going to be based on these following rules that you see here. Okay, so there will be assignment, as I said, maybe 10 to 12 assignments. I'll try to have almost one every week, and I might have quizzes, 10 minutes, 15-minute quizzes during the lecture hour, typically towards the end of the lecture. Okay, so those will all be worth 20% towards the total weight of this course. Then there will be 2 midterm exams. I have already indicated the date, September 25th and October 30th, in class, during the class hour, and each one would be worth 20% towards the total weight. And then there will be a final exam that will be worth 35%. And then I call an e-portfolio, which is worth 5%. And what I expect here is each one of you to develop an e-portfolio, an electronic portfolio, that tells everybody else in the world something about you, what your interests are, what is your CV, what have you done in the past, what have you learned in this course. You may want to display things that you have done in this course, programs to the entire world. So the basic idea is, how do you construct, how do you put together a web page that describes your activities to the world. It might be useful, this technique might be useful when you're in the senior year, you've done a nice senior project and you want to showcase this with nice animations and stuff for simulations using chemical process software to your potential employer during an interview, for example. Okay, so the way that we communicate is changing. It's not just printed CV that you're going to give, but you can give a very rich multimedia content about yourself. And so we will learn how to construct such electronic portfolio. After all, this course is about use of computers in chemical engineering. Okay, so we will introduce a variety of software, but MATLAB is going to be a major portion of it because it's a very nice environment, interactive environment for learning how to program, learning some of the concepts of programming. Okay, and then we will introduce you to HYSYS or Aspen. Okay, that's a software that chemical industry uses a lot. And in the next course, 2176, you will learn what sort of ideas go into developing a software package like that. That is, what are the mathematical models, what are the computer solution techniques. So we will learn something about computer programming to be able to achieve that in the next course. So 2176, for example, should have 2160 as a prerequisite. Okay, so e-portfolio will be worth about 5%. There is no lecture or anything on that. What I'm going to do is show you through a demonstration on how to construct an e-portfolio using Microsoft Word as an example and how to publish it. This will be a separate recorded video from my office that I will put on Moodle during the next 2 weeks or so, and then you'll be able to listen to it, learn from that. So this also teaches you how to learn things on your own using resources from the internet. So by looking at that, you'll have to construct your own e-portfolio and upload it to the LSU server, web server. And towards the end of the course, I will take a look at every one of the e-portfolios that you have submitted, assess it, and then give you marks out of it, and that will constitute 5%. Any questions? Are you able to hear me in the back? Are you able to see what's on the board? Okay. The assignments you will submit online. So I expect you to prepare a file. It could be Word or whatever document, or it could be written but then scanned. But I want a single file that has the answers, the solutions to the particular assignment to be submitted on Moodle. Okay, then the TA will download it and mark it, and then you will see your marks for each one of the assignments as a spreadsheet in Moodle. So one of the things that I have asked you in Moodle is to give me your, what they call the keypad number. Okay, this is the number I guess that you use in Flickr or something, but some kind of a mnemonic, I don't want to use your LSU ID, I don't want to use your name whenever I post the spreadsheet that has your marks and rank. I did give feedback throughout the course, so you will find a ranked list of your marks after the first midterm, after second midterm, etc. So that to know where your marks are, there are a couple of ways. If you know all the marks that you have tried in exam 1 and exam 2, you can try to match and say, okay, that must be me. It's very unlikely the two will have exactly the same marks. Or if you give me this mnemonic key of 6 characters, by filling in a form online from Moodle, then I will put that in the spreadsheet as one column so that you know this is my code, so these are my marks. Okay? The assignments typically will be due a week from the day I hand them out, and typically it's going to be Tuesday to Tuesday. So there is one assignment already up on Moodle that you should download today, and it will be due next Tuesday by 4 o'clock on Moodle, electronically submitted. So these learning outcomes and stuff you can read basically after you go through this course. You should have some rudimentary knowledge of what programming is. How many of you have taken any kind of a programming course in high school or first year? Only a few. What kind of course did you do? Pascal? C++. That's very good. So you should find this course very easy. Anybody else? Somebody put up your hand. Yeah? C++. Some Java. Okay. So you guys should find this course fairly easy to do. I hope if you grasp all the programming concepts in there. The programming part. We will, of course, introduce you to some of the simulation aspects like HYSYS and COMSOL. And that's just to show you what is the status of use of computers in chemical engineering process analysis. Okay. General rules. Do not use cell phones in the class. Please turn them off. Do not engage in any disruptive behavior in the class. When assigned work is not completed on time, you don't get any credit for that. And more importantly, you can read the rest of it. Class participation is strongly encouraged. This pledge, I want in every work that you submit, in the exams, in the assignments. It's something that I learned when I was in graduate school, where they basically give you the exam, say take it home and do it, but with this pledge, and then bring it back. And the pledge basically says that you have not cheated. Okay, so the rules are you will use 2 hours to do this exam, then maybe 2 hours to do this exam. We are going to have a take-home exam in this course, but that's a general idea. So it basically says I pledge that I have neither given nor received any unauthorized assistance on this assignment, exercise, or examination. Okay, so I will tell you what are authorized help as we go along. Okay, so it's perfectly okay, for example, for 3 of you to get together to discuss a problem, or if one is stuck and the other one can kind of try to help out the concept. But what is not acceptable is 3 of you to sit in front of a computer and do the assignment, and there is one person typing and the 2 other people watching it, and then print 3 copies and put your name and submit it. That is not acceptable. I want each one of you to sit in front of the computer and do the assignment on your own. You can have all the consultation and all the help that you want with each other before, but when you are doing it, there is value in doing it by yourself, not just observing. Okay? So I want each one of you to do the assignment on your own, after whatever consultation that you think is necessary with others or with me. You're always welcome to come to me. And if you're stuck in an assignment, again, you're always welcome to ask other people for help or come to my office and ask for help. I'm ready to help anytime. Okay? But copying something from somebody else without understanding to say that you have completed the work is not acceptable. And this pledge basically follows an honor system, saying that you have not done that. And, well, if the TA notices that 2 are identical photocopies, he will flag that and bring it to my attention. And whenever I see that there is strong evidence of 2 people copying, and this always happens in every class with a group of 2 or 3 people, and I give a 0 for all concerned, because I'm not going to get involved in the issue of judging who copied and who helped, who understood, who did not understand. I don't want to get involved in that. If there are 3 identical or 2 identical assignments, all the persons concerned will get a 0 for that particular assignment. And if there is a repetition of pattern, then I'll probably have to report it to higher authorities, because plagiarism is not tolerated according to university policy, College of Engineering policies. Okay? So these are some of the syllabus material that we will cover, and you can kind of go through that. And there are some recommended texts that I've given you. There is no required text. These are some of the recommended texts, but one that I gave you earlier is probably the cheapest one that you can buy, an electronic version of it. Any questions? Absolute silence. So that can only mean 1 or 2 things. And have you understood everything I've said, or have not understood anything I've said? Yeah.
For the pledge, are you requiring us to type that onto anything we make, or is that something that's going to be on the exam? So it's pre-required.
Say that again?
The pledge, you said that we
the pledge.
That up on everything.
That's a good question. In the exams, I tend to put that in the exam paper itself. So all you need to do is sign. But in assignments, I don't have a standard template that I put in every assignment, because I don't know how you would do it. You might do it on a piece of paper and then scan it. Or you might go in front of a computer, do it, and then cut and paste into a Word document and upload it. Okay? So what I want is type that. Okay? And then at least electronically sign your name. Okay? So it doesn't have to be your physical signature, but type your name and ID, that signifying that you have honored that system. That's a good question. Yeah. Any other questions? Okay. In this lecture, the first lecture, we're just going to talk in general terms. What are computers and what is a number system? And I might get to the point where I introduce you to MATLAB, how to start MATLAB. And MATLAB is a very powerful program. MATLAB stands for Matrix Laboratory. It started about 20, 25 years ago, I guess. When I was a graduate student, that didn't even exist. That shows you how old I am. So it is about 2 decades, 2.5 decades old. And it has evolved very rapidly. And you will find, of course, most of the chemical companies that you might ever work will have a PC, which is connected to the plant itself. And you might have something called DCS, Distributed Control System. Has anybody been to a plant, co-op, or anything? Some of you have. Where did you work? Anybody else? So have you used any of the software? Have you seen any of the software that they use? What kind of software do they use?
Chemical processing. I forgot what it was called. It was like to show like the flow of all the chemicals going through and the temperatures.
Right.
Radiation, just like that.
Exactly. So a chemical engineer basically manages a chemical plant, right? What does a chemical plant do? A chemical plant basically takes raw materials, chemicals found in nature, and converts that into useful products. And Baton Rouge, Louisiana, is a very good place for a large number of chemical companies that are situated here. Refineries, gas plants, petrochemicals, polymers, for example. All these plants are around us. So if you take, for example, a refinery, what does a refinery do? It takes the oil that we dig from the earth. Petroleum engineers do the job of finding it, digging it, and bringing it out to the surface. And once it comes to the surface, we take over the crude, and then we put it through a refinery. So a refinery has distillation columns, heat exchangers, pumps, etc. Okay? So it uses various principles of differences in properties. For example, if you heat the crude is actually a mixture of many chemicals, many hydrocarbons. You can separate them based on their boiling point. So you can take gasoline, you can take jet fuel, diesel fuel, etc., separate them. So typically these days what you will find is, because computers have played such a big role, you'll have something called a distributed control system. So you just you don't go into the plant. The plant will have operators on the floor, but as a process engineer, you're going to be sitting in front of a computer and you will see these nice diagrams flashing in front of you with the pumps, and you'll have controls. You can say, increase the pump pressure or the flow rate, just typing in the number into a small box, and then it sends a signal, and the pump power is increased, for example. Or you may just want to monitor the temperature or the flow rate of gasoline. Okay? So we interact with computers, and the distributed control system is one interface between you and the chemical plant. Then as a process control engineer, process control is a subdivision within chemical engineering, you might want to actually control the plant. So you might say, oh, I'm producing so much of gasoline, but the demand is so much in summer, I want to increase that. Okay? So what changes should I make to the process so that I get a different kind of a product distribution? So a control engineer might come into play to, again, interact through computers. And you will learn in the fourth year, the senior year, a process control course where the mathematics behind it, the models will all become familiar. So in order to prepare you to understand those courses, this course is going to lay the groundwork. Something about computers, what do they do? We understand something basic about how computers function, how we can program them. Okay? Other software that is commonly used is called HYSYS and Aspen. Those are process simulators. So they will allow you, for example, to look at if there is a crude that is coming from Texas and next week you have a tanker coming from Saudi Arabia. It's a different crude, and you want to predict what would be the changes, how should I change the operation of the plant so that I get the same amount of gasoline using two different feeds. So the simulator will allow you to simulate the process, and then I try to find out what conditions you need to achieve the goal that you need. So there are process simulators, there are process control operations, and there are simply data acquisition systems that acquire the data from the plant, temperatures, flow rates, composition, etc., and display it to you, and then log them on into the computer. So the basic question is, how do the computers do these things? Okay, that's going to be our goal. Now, computing we have been doing for a very, very long time. Does anybody recognize what that is? Abacus. Okay, it's basically a mechanical counting machine. It has been used for 2,000 years or so. Okay, and you recognize abacus. How about this one? It's amazing. So you actually know what a slide rule is, because slide rules are not available these days. How many of you have seen a slide rule? Wow, that's very good. I did entirely rely on slide rule in my days as a student because calculators were not there. Okay, so we didn't have calculators, so we had to do all the multiplication, division, etc. by slide rule. So it is a device that allows you to do multiplications and divisions using logarithms. Essentially, what happens when you use logarithms? Do you kind of understand what logarithms are? Well, the basic idea is the following. When you have multiplication of two numbers, when you express that as an exponent, it becomes, multiplication becomes addition. Okay, this is one of the strategies that I use. Okay, I try to stop, and if somebody says addition, then I say, okay, everybody understands that, and then move on. Okay, a good example: 10 to the 5 multiplied by 10 to the 3. What is that? It is 10 to the 8. So you have product of two numbers. Okay, but when I express them as a power to some base, then it simply becomes 5 plus 3. Logarithm essentially uses this idea, log to the base 10, for example, uses this idea to convert multiplications into additions. Of course, when you do the addition, you need to come back to the natural world, from the logarithmic world, okay? And you have something called the anti-logarithm, okay? Inverse logarithm. So you do the additions in the logarithmic space and then come back to the natural world by taking the inverse. And what this slide rule does is, addition is simply displacement. So if I have one part that moves, another part that is fixed. So if I have, for example, a reading here, and I slide it, and I measure the distances, 2 inches plus 3 inches is 5 inches. So along those, I will have some numbers. So when I multiply two numbers, all I have to do is position these two and read the third number as a distance from there, and that will be marked already in the anti-log space. So all I have to do is read the number, and I get the product. So finding the product of two numbers is simply sliding this and following the rule to calculate what the number is. Of course, there are errors in the number of precision that you can get, because you can read only to so many digits from there. Okay? The slide rule is essentially a computing device, a mechanical computing device. The first electronic computing device is something called EDVAC, Electronic Discrete Variable Automatic Computer. It was built only in 1949. It's only a few years older than me. Okay? And there are some interesting statistics that I picked up from the net. I guess here it is. The computer has 6,000 vacuum tubes, 12,000 diodes, and consumed 56 kilowatts. A lot of power compared to a cell phone. How much power do you think a cell phone consumes? Maybe a watt or two, right? It doesn't consume a lot of power, whereas this one consumed 56 kilowatts, 56,000 watts, and weighed 17,300 pounds. That's a computer, the first computer. And how fast did it do the calculations? It did one multiplication in 2,900 microseconds. That is 0.029 seconds, for example. One multiplication, that's still fast compared to human beings, right? It can do the multiplication in 0.029 seconds. What it basically means is 1 second, maybe it can do 30 calculations, 30 multiplications. That was the speed of the computer then. What do you think a modern computer can do? How fast can it do the calculations? Anybody guess? In 1 second, how many multiplications do you think a modern computer can do? Couple of thousand? Anybody else?
How modern? Are we talking about like a...
The latest computer that you can get hold of, the fastest computer that you can get hold of.
No idea.
No wild imaginations, wild guesses? Million? We are getting closer to the truth. Okay? That is the latest computer that the Lawrence Livermore Lab has. Okay, Department of Energy. You know how many computers there are? 1.5 million computers connected together. So they work together. Okay? In 1 second, they can do, where do I have the numbers? I wrote down somewhere. Here, 1.5 cores. That's the number of processors that they have. And it can do 16.3 petaflop. You know what a petaflop is? We have kilo, mega, giga, tera, and then peta. Okay? 10 to the 15 calculations. 10 to the 15. 10 followed by 15 zeros. That many multiplications in 1 second. Okay? You might now wonder, why do we need such huge computers? Do I have problems that require that many multiplications, that many calculations in 1 second? And these computers run 24 hours a day, 365 days a year. So what kind of problems do they solve? Okay? These are engineering and science problems. In chemical engineering, there are problems that require that much of a computing power. Of course, Google has also of the order of 1 or 2 million computers spread throughout the world in different centers to serve just a search function. Right? But of course, they have billions of people using their searches, and you see instantaneous response whenever you type in. The reason is that much of computing power is behind this. So what we want to do in this course, in this lecture, the first lecture, is get some idea of the terminologies that are used to describe computers, to understand the magnitude of the power that we have with modern computers. Any questions? That is the largest computer. Okay? Today, the best computer that can do 10 to the 15 multiplications in 1 second. And most of the weather prediction, for example, or when we have the oil spill, the problem is still not understood. We could not predict how much of oil was even being spilled. Okay? So if you are worried about predicting where the oil is going to end up, there are no computer models that are able to do it today. And in fact, that's one of my current research interests. We're trying to work on building some of the models. So my main research interest is in computational models for studying chemical processes, whether they occur in nature or in a chemical plant. That is a typical desktop computer that you might have at your home, and basically 1 or 2 or 4 or 8 cores. Okay? And they can do calculations of the order of gigaflops. Even those computers in 1 second can do 10 to the 9 multiplications. Okay? So these are really very fast processors, consume very little energy. That computer may consume 100 watts, 150 watts power, compared to 46 kilowatts that the earliest computers were consuming. Okay. The next question we might want to ask is, what is inside a computer? Okay, so that we can, most of you will be using computers. That is for granted, whatever the job it is. Okay, you're going to be using computers. Even if it's a secretary's job, inventory keeping, whatever it is, computers are dominating the way that we live our lives. Okay, so to be able to intelligently talk to the support person. So if suppose your computer crashes, okay, you need to be able to call the support guy and tell what the problem is, what is the nature of the problem. Okay, I saw a cartoon once. My secretary had it. This was several years ago, and normally you will have this message or a prompt which says, "Hit any key to continue." Okay, that is any key on the keyboard. If you hit any key, it will continue. So it will pause and will give you a message and hit enter or something. And the cartoon had a big hammer hitting on the keyboard, because that's how much he hated computers. There was a time when computers invaded the secretarial world, and before that they were using a typewriter. So when they were asked to use these computers, this is what it meant to her. Hit any key to continue meant hitting this with a hammer, right? So you need to understand, you need to be able to communicate intelligently with the support person. And you need to use the computers intelligently. Hopefully by the end of this course, you will develop that smartness, okay? So the question is, what is inside a computer? Again, some of you may find these, you might have taken a summer course where you actually rip apart a computer and put it together. Has anybody constructed, put your own computer together? At a stop? So you will know about all these parts that I'm talking about. Very briefly, what is this part? Can you identify what that part is? It's called the motherboard. Okay, so this is a schematic of what a motherboard is. This is actually a photograph of what a motherboard is. It's a main board. All the laptops that you have, all the desktops that you have will have an electronic board where every connection is laid out, printed circuit board, PCI, and you have a central processing unit. Okay, and the specifications here would be, this is where we say we talk about 2-core, 4-core, 8 cores or whatever in a central processing unit. So the central processing unit is like our brain. Okay, it gets signal from various parts of the body through the nervous system, and it processes it attached to the memory, and sends out signals back. So when I'm writing something or when I'm talking, I'm looking at you, so the visual signal goes from my eyes to the brain. Okay? And if somebody is puzzled, are you guys finding that distracting? So the human body is kind of a computer. There are a lot of analogies. Okay? So I'm getting signals from my ear, from my eyes, from my senses, whatever, and the signal goes to the brain processes it and responds to it. So when I want to write, the brain sends the motor action, all the signals, and that make me write. So in the same way, the computer has the central processing unit, the CPU, that receives signals and instructions on what to do with data. So it collects data and collects instruction, and the instructions will typically be, computers can do very little things if you think about it. The only thing is they can do so fast. Okay? Essentially a CPU, what can a CPU do? Those who have put this computers together, do you have some idea? What does a central processing unit do in a computer? We can make it do almost anything we want, but fundamentally it understands only very few operations. Okay? So this is called the assembly language or the instruction set for a central processing unit. There are probably about 100 to 200 instructions that it can understand. Okay? So what it can do is it can move data from one memory location to another memory location. So fetching or putting it back. So move data and then operate on data. What kind of operations can it do? It can compare, for example, is this data the same as this data? Is this number the same as this number? So those are logical operations. You can compare these two numbers and decide this is bigger than that, smaller than that, yeah, it is equal to that. The other thing that it can do is it can take those two numbers and do arithmetic operations. It can add these two numbers, subtract two numbers, multiply two numbers, divide these two numbers. Okay? If you think about it, a central processing unit is capable of doing only these kinds of operations, very elementary operations. But they can do it so fast, we can then write big programs that will allow the computer to recognize, a pattern recognition, for example. You show a flower, it takes an image. When it takes the image, when our brain takes the image, what does it see? You can think of it as sees pixels, dots of images. Okay? As most of the digital computers, the cameras do the same thing. It digitizes, it takes this whole space and constructs into dots. For example, what you see on the screen. How does the computer display this image onto the screen? What does that data projector do? It has 2,000 lines along this and about 2,000 lines in the vertical direction. And there are dots in each one of them. These are called pixels, right? So it controls the intensity of each pixel and it controls the color of each pixel. Okay? So it is digital information. And so we already have to display this, it must have 1 million pixels that are being displayed continuously, 30 times every second. Okay? So if I move this, it immediately knows that these pixels have to be turned into red. Okay? So the central processing unit's role is to carry out these instructions. Okay? Now this is a very large picture in terms of when I write this, it displays that on the board, but underlying that there are thousands of lines of code that digitizes this information, transfers the signal to the projector that shows the same line. Okay? Digital processing is done typically this way. Another example, let's talk about a chemical engineering. So you have a distillation column. You know what a distillation column is? For those who have not yet been, maybe they're only getting introduced to chemical engineering, those who are not yet seen, in fact, you have seen it, but you probably don't recognize what it is. These tall columns, as we drive towards the airport in the Exxon plant, okay, are distillation columns, the tall towers, okay, and they take the crude and break them based on temperature, based on volatility into different products. So what I would like to do, for example, as a process engineer, is know what is the temperature at one point. So I have a thermocouple. Now, what is a thermocouple? It's a device that measures the temperature at a particular point. So you can now ask the question, it's an instrumentation problem now. In process control, you will learn how these instruments work. So a thermocouple is essentially a device which has a very fine tip made up of two different metals. And when you expose that to a hot environment, the two different metals produce different number of electrons. And there is a differential in that, so it produces a millivolt difference, which is proportional to the temperature. So all I get from a thermocouple is a voltage signal. And that voltage signal is amplified, converted, and sent to the digital control room. So, and that is converted into a temperature, and that is displayed on the monitor. So there are conversions of signal all along from the distillation column into what is displayed in here. So we need to know how these conversions take place. How are these numbers represented in the various units? Okay, that's one of the things that we are going to do today. So the central processing unit is the most important part, equivalent to our brain. And RAM, these are the positions where you store memory. So what is this? This is a memory chip. If you open the computer, you will find these chips inside that. So a memory chip like that can hold typically 2 gigabytes or 4 gigabytes of information. So when you go and tell the IT guy, hey, my computer is crashing all the time, I need to increase its memory. You might ask, how much do you have now? I have no idea, right? So you should be able to say, okay, currently I have 4 gig, I need to increase it to 4 gig. Okay, so that basically means you need to increase the capacity of these chips. 4 gigabytes. Now, what is a byte? We are going to see today what a byte is. Okay, byte is a certain piece of information. So 4 times 10 to the 9 bytes of information that I can store in one of those chips. So, as I said, the CPU can move data fast. So from this chip, the data is moved to the CPU. The CPU is here. So it goes back and forth. And then there are also other signals. For example, I might have a hard disk that is connected to one of the PCI slots. The hard disk has much more capacity, a terabyte. Okay, so that's where we will document all the data that is coming from a plant, for example, temperature for the last 1 year from one of the plant units. Okay, so a hard disk is a disk, this is a magnetic device which can store information permanently, even if you turn the computer off. Whereas this DRAM will lose the information. The moment you turn the computer off, it forgets about whatever is stored in that. When you boot the system, when you turn the system on, the operating system is loaded into that DRAM. And from there, instructions go to the CPU, data go to the CPU, things are achieved, and they go back. So this is kind of a temporary storage, a fast access. The RAM can write and read information from the memory much faster than a disk can. Okay? So this is a fast access, and then you have your disk, which is a much slower access. And of course, you have an Ethernet connection to the world or to the plant. Okay? So there are many other outputs. For example, a keyboard is connected from there. So when you type, the keyboard information goes to this, through the memory, into the CPU to understand what you are typing. The mouse, all these external connections are done through these slots that you have. Those are the essential elements of a computer. Okay? There will be one connection to the screen itself. Okay? Those are called input-output. So there are programs that manage this input-output information to a variety of devices from a computer. Any question? So if I ask you to write a very brief description of what are the computers, what are the essential elements of the computers, will you be able to do it now? Okay. That is a hard disk, a drive. So it's essentially a circular disk with a magnetic coating. Okay, and you have a tip there, and the tip basically scans that surface. This disk will spin. It could be an optical disk as well, in CD-ROMs, DVD-ROMs, etc. But the hard disk typically is a magnetic device. Now, one of the things that we need to recognize as we are talking about these magnetic and optical and diodes and electronic, they all have some feature that is very common to them, and I'll talk about it very soon. We also talked about pixels, okay? The same thing with that. So there's a modern laptop, and the way that we are communicating with tablets is even different from the way that we communicate with a laptop. Laptop, we use keyboard and mouse. With a tablet, we use a pen, or you just touch, okay? And pretty soon we won't even need that, we just talk, and it will talk back to us, okay? So there is enormous amount of information processing when I talk to a computer and it understands. Okay? It takes the digital signal, it takes the signal that comes from the mic, which is actually an analog signal, converts it into digital signal, and tries to understand what I'm saying from the sound. Okay, and converts it into a natural language and then compares it against the database, and it knows what I'm asking. And then it does the search and brings it back. Okay, so enormous amount of processing power is needed to support these input-output functions. Okay, and that's why we need these computers to be very powerful, to be able to do gigaflops of calculations. So this is a conceptual layout of what happens, and I want to just set the framework of at what level we are going to work on. So all these are just introductions. So the hardware is what we have been talking about. This is the computer itself, whether it's a tablet or a PC or a desktop or the supercomputer in Lawrence Livermore lab. The hardware is the physical hard device with the central processing unit, the input-output units, the memory, etc. On top of that, we have something called an operating system. These operating systems provide all the input-output functions. The program control, the logic, the comparison, the multiplication, the addition, etc. The file system that is connected to the hard disk. Okay? The communication system, any error messages. Okay? So security. So there are a lot of these functions that are kind of at the lowest level of the operating system. And onto that you have at the top the user interface. That's what we interact with. Okay? When I see this, I see, for example, if I want to close this, I just click that. That's a user interface. That's a graphical user interface. When I click that, a signal goes, but goes to the top level of the operating system, which is transmitted all the way, and ultimately it says close this window. And it responds by closing that window. To search where that window is. There. But what, as chemical engineers, we are going to do is not worry, except to have some rudimentary understanding of what a hardware is, what an operating system is. We are going to focus on the user programs. Okay? The user programs are all the programs that we run from a computer. Currently, for example, this program has something called PDF annotator. That is a program. What does that program do? It opens up any PDF file. It allows me to write onto the PDF file. It allows me to annotate on that. Okay? So that's a program that I am interacting with. That's a user level program. There is another program called Camtasia. What does it do? It actually records what happens on the screen, records the voice, and stores it on the hard disk so that later on, once I'm finished with the course, I go to my office and convert that into an MP4 file and upload it to Moodle so that you can listen to the whole lecture again if you want. Okay? So that is a user level program, okay, that is running in the background silently. And I'm going to start a program called MATLAB, which is what we are going to see. Now, MATLAB is available in the chemical engineering building. There is a computer lab on the second floor. It is also available in all the labs in the College of Engineering building, the Patrick Taylor Hall. But it may be available on other campus computer labs as well, including the library. I cannot guarantee that. But College of Engineering has license to MATLAB. Chemical engineering has license to MATLAB. You are encouraged to buy your own student edition of MATLAB if you want to be independent of it and work from home. There is also VLab. Are you guys familiar with VLab? You have not used VLab at all in any of your first year courses? Okay, then I need to find out what VLab is. I just know about that something called VLab exists. It is essentially a virtual lab. That means you can connect to it from your own laptop. If you have a laptop, you can connect to it, and it gives you a virtual environment where you can access all the LSU software onto your PC through this VLab interface. Okay? It's a fairly easy thing to use apparently, but it is not available for faculty members. It's available for students. So only you can access it. I will try to find out what the instructions are and put it on Moodle so that you can access VLab and access MATLAB from that if you choose to. But if you go to any of the physical laboratory locations, computer labs in chemical engineering or Patrick Taylor, go through the search process from the start window, you will find MATLAB. That's an icon that you need to remember. So one of the nice things about capturing this video is you can know. If you forgot where it is, you can search. So when you start the program, it starts another user level program, okay, called MATLAB. So this computer now has many user level programs that are running on the operating system. What is the operating system I'm running on? Windows 7. Okay. What is the hardware I'm running on? Some sort of an Intel processor. The CPU is Intel, and I have a laptop. A motherboard is also made by Intel. So when I start MATLAB, this is the window that I get. Okay. So now I can interact with MATLAB, and I can start doing calculations with MATLAB. Okay. So let me just give you in the remaining 2 minutes that we have, or 1 minute, what are the basic elements of this MATLAB window, graphical user interface window. Okay. So you see an area called command window. There are several windows. There is a window called current folder window. There is a window called details. Okay. And there is a window called workspace. And there is a window called command history. Each one of them is a window that is controlled by MATLAB graphical user interface. MATLAB, as I said, is an interactive environment, meaning you can interact with it. For example, in the command window, you can issue a command. What is a command? The command may be simply A is equal to 5. So when I type this A equal to 5, what I'm telling MATLAB is create a variable labeled A and store the value of 5 in it. So A equal to 5 is an assignment statement. The concept is I'm assigning a value to a variable, and then I hit enter. When I hit enter, it tries to interpret. This is why it's called an interpretive environment, interactive environment. So it looks at what I type. I typed A, I typed equal, I typed 5. So it says, okay, he wants to create A and assign value of 5. So it echoes back. It says, okay, I've done the job. What is the next command, sir? It's waiting for you for the next command. And we'll pick it up in the next class. I guess I'm typing already. Okay?